Hey, we've been studying techniques of integration all semester. Now it's time to turn to applications of integration, and our first one will be volume. And here's a picture that describes the basic idea. We have a curve f of x, and we look at the area under the curve and above the x-axis over some interval, and in this case it's between 1 and 4. And we consider what happens if we take that area and we rotate it about the x-axis in 3 dimensions to come up with a solid figure such as the one depicted on the right-hand side in this picture. And what we're looking for is a formula to compute the volume of the solid that you get when you do that. And if you recall, when you first looked at the area under a curve, you did it by breaking the curve into a bunch of thin rectangles that approximated the area and adding up the areas of those rectangles to come up with an approximation of the area under the curve. And then you let the number of rectangles go to infinity so that the thickness of the rectangles went to 0 and took a limit to come up with the precise area under the curve. Well, we'll do something very similar here to come up with the volume of the solid that we get after we rotate this area, and we start the same way with a thin rectangle like I've drawn here in the picture on the left. And if you consider what happens to that rectangle as you rotate the area about the x-axis, you get this circular disk, this slice of the volume, something like what I've drawn in the picture on the right. And what this circular disk is, in more precise mathematical terms, is it's a cylinder with a very small height. The very small height we can call h. It's the thickness of the cylinder in this case, because the cylinder is turned on its edge. And in addition to its height, a cylinder has a second very important dimension, its radius. In this case, I've labeled it as r, which is the distance from the x-axis to where the cylinder hits the curve f of x. And if we imagine that we have n of these rectangles that we are rotating about the x-axis, and that the one that we're looking at right now is, say, the ith rectangle, which occurs at some x value that I'll call x sub I, which might be the left-hand endpoint or the right-hand endpoint or some point in between, it doesn't really matter. Then the radius of the cylinder is simply f of x sub I, because that's where the radius hits the curve f of x. And there's a well-known formula for the volume of any cylinder. It's pi r squared h. And since the height of this thin cylinder is the width of the original rectangle, it makes sense to call it delta x, the change in the x value. That's the width of the original rectangle, giving us an expression for the volume of the ith thin cylinder as pi times f of x sub I squared times delta x. And if we now imagine breaking the original area into n thin rectangles, and then adding up the volumes of the n thin cylinders that we get an approximation of the volume, which is the sum of the volumes of those n thin cylinders. So this is all this sigma notation or summation notation means. It means start with I equals 1, go to I equals n, and add up all the terms. So this is pi times f of x1 squared times delta x plus pi times f of x2 squared times delta x, all the way up to pi times f of x sub n squared times delta x. And that gives us an approximation of the volume of this region. But of course, just like you did in your Calculus 1 class with area, we're not really interested in an approximation of the volume. We're interested in the precise volume. And we define the precise volume as the limit as n goes to infinity of these approximations. In other words, what if you took infinitely many thin disks, so they would have to be infinitesimally thin, and added them all together? Well, as you take more and more, you get a better and better approximation, and so it's reasonable to say that as you take the limit as n goes to infinity, as you take infinitely many of them, you get the precise volume. And so here we have an expression for the precise volume of this region. And that limit should look extremely familiar. It's precisely the definition of the integral from a to b of pi times f of x squared dx, where in this case the a and the b are 1 and 4, just because our picture happened to have 1 and 4 explicitly specified. But from any point, wherever the region starts a to where the region ends b, this is an expression for the volume. The delta x became a dx, essentially, as n went to infinity, and the summation sign became the integral sign as we took the limit as n goes to infinity. And so what we've just come up with is a formula for how to find the volume underneath some curve of any function between any 2 points a and b, or at least any function that we can integrate between any 2 points a and b. We may as well do this particular example that we're looking at here. This function is not any arbitrary function. It is actually a graph of the function f of x equals the square root of x. And to find the volume of the solid that you get when you rotate the area under the curve y equals the square root of x from 1 to 4 about the x-axis, and so get the picture that you see on the right, we apply this formula that we just came up with, and we get that the volume is the integral from 1 to 4 of pi times the function, which is the square root of x, all squared, dx. And pi is just a constant, so we can pull it outside the integral, and the square root of x, all squared, is just x. And integrating, we get pi times 1/2 x squared, evaluated from 1 to 4. And after you do the arithmetic, you get that the volume is 15 pi over 2. Okay, you're going to try this one. I'm going to start you off. This is the way the problems are generally presented. Find the volume of the solid generated by rotating the region bounded by some curves. And in this case, it's y equals x squared, y equals 0, and x equals 2 about the x-axis. And in some situations, like simple ones like this, you might be able to get away with just starting in on the problem. Terrible idea. You should always draw a picture first. They are going to get more complicated, and the picture is going to help. The pictures are not hard to draw. Let's do this one. This, more or less, is the graph of y equals x squared. X equals 2 is a vertical line passing through, no surprise, x equals 2. And y equals 0 is the x-axis. And so those three curves taken together really do uniquely specify some region, and it's the region that I've shaded in here in light blue. And then it takes a little bit of imagination and perhaps a little bit of drawing skill, and maybe more than I can muster, but we'll see, to imagine what happens if you take that region and rotate it about the x-axis. So you imagine that it is fixed to the x-axis along the bottom, and then you grab it by that top corner and you pull it out of the board and towards you, or out of the screen and towards you, and flip it around and bring it back and flip it back through your screen and up the other side until you have this three-dimensional picture that maybe looks something more or less like this, sort of like the end of a trumpet sticking out, blowing to the right, but it's solid all the way through. And you might ask, why did I need to draw that picture in order to compute the volume? And the answer is, for this particular case, you probably didn't, but in the future, as I had mentioned, they will get more complicated and the picture will be a big help. In this case, all that you really might have gotten out of it is that the integral that we're interested in is from 0 to 2. That's where this solid shape is. It starts at 0 on the left and goes until x equals 2 on the right. Okay, I promised to let you do it, and I've probably already done more than I should. Take a moment, pause the video, compute the volume of this solid. When you're ready, start it up again. By the formula, the volume is the integral from 0 to 2 of pi times the function, which in this case is x squared, all squared with respect to x. And I should point out that at this point we have done all the hard work, not that it was such hard work, but it's setting up the proper integral for the volume that is the whole trick. This is a very easy integral now that we have it set up. And it's easy enough that I won't go through it step by step. I'll let you check your work. You should have come up with the answer of 32 pi over 5. Okay, I want to show you one more example just because it's super cool and I can't resist, and that is we can use what we have just learned to come up with a formula for the volume of a sphere of radius r. And what we're talking about is taking this circle, the circle x squared plus y squared equals r squared, and rotating it about the x-axis to get a sphere. The problem is that this is not a function. We haven't done calculus on anything that isn't a function yet, and so it's a little bit tricky. And how we deal with that is we just look at the top half of the circle. If you solve algebraically, you get that y is the positive or negative square root of r squared minus x squared. But if you just look at the positive square root of r squared minus x squared, now that is a function. And when you rotate that about the x-axis, you get the same region that you would if you rotated the entire circle about the x-axis. And so you get the same sphere, the sphere of radius r. And since it has radius r and is centered at the origin, it crosses the x-axis at both r and negative r. And so our formula for the volume tells us that the volume of the sphere is the integral from negative r to r of pi times the function, which is the square root of r squared minus x squared, all squared with respect to x. That simplifies beautifully because the square root of anything squared is just that anything. And now this is very simple to integrate. You have to keep in mind that the r is just a number. And so if it helps, you go off and you do this with r equal to 5 or r equal to 7 or something. But it's just a constant. It's not the variable. The variable is x in this case. Which is why when you integrate, you get r squared times x minus 1/3 x cubed. In other words, r squared, just a number. If it had been a 5, 5 squared is 25, and the integral of 25 is 25x. Same idea, integral of r squared is r squared x. On the other hand, x is the variable. When you integrate x squared, you get 1/3 x cubed. And all that's left is to do the arithmetic or algebra of evaluating this from negative r to r. You have to be a little bit careful with your signs. And after you do all the arithmetic, you get that the answer is pi times 4/3 r cubed. Or in its more common form, the volume of a sphere, 4/3 pi r cubed. And you've probably seen that before, and you might have even known it already. You might have had that memorized, that the volume of a sphere is 4/3 pi r cubed. But how did you know? You knew because somebody told you at some point that that was the volume of a sphere. And as far as you knew, none of your math teachers had ever lied to you before, although they probably had. But this is where it comes from. Now we just figured it out on our own through the calculus that we have so carefully learned over the past, semester and a half or thereabouts is enough to show why the volume of a sphere is 4/3 pi r cubed. So pretty cool. Okay, you are now in good shape to do the first of what will be 3 homeworks on volume, cleverly called Volume 1. So give that a try. Don't forget to have fun, and I look forward to seeing you in class. Bye.